Hello and a very good afternoon, guys. How are you? Hope you are pretty fine. As you can see in this lecture of mine, today I am going to discuss diffraction from periodic structure and diffraction as an investigating procedure. This is Dr. S.K. Jaiswal from the University Department of Physics, T.M. Bhagalpur University. Now to start with, as many of you might be knowing the fact that direct imaging of atomic structure is nowadays possible using the high resolution electron microscope, the field ion microscope, or the tunneling microscope. Nonetheless, when we wish to determine an unknown structure or make exact measurements of structural parameters, it is necessary to rely on diffraction experiments. The greater information content of such measurements lies in the fact that the diffraction process is optimally sensitive to the periodic nature of the solid's atomic structure. Direct imaging techniques, on the other hand, are ideal for investigating, say, point defects, dislocations, and steps, and are also used to study surfaces and interfaces. In other words, they are particularly useful for studying features that represent a disruption of periodicity. For performing diffraction experiments, we can make use of various types of probes. For example, the X-rays, the electrons, the neutrons, and the atoms. These various types of probes differ widely with respect to their elastic and inelastic interactions with the solids, and hence their areas of application are also different. For an example, atoms whose uh, particle waves have a suitable wavelength for diffraction experiments, but they do not penetrate into the solid and are thus suitable only for studying surfaces. The same applies to a lesser extent to electrons as well. Another important quantity which differs significantly for the various probes is the spatial extent of the scattering centers. Neutrons, for example, scatter from the nuclei of the solid's atom or atoms, whereas X-ray photons and electrons are scattered by the much larger electron shells. The size of an electron shell is about 10,000 times the size of a nucleus. So despite this and other differences which we may deal with in some later video, it is possible to describe the essential features of diffraction in terms of a single general theory. Such a theory basically would be quasi-classical in nature, since the scattering itself is treated classically in these theories, or in this theory rather. The quantum mechanical aspects are treated purely by describing the probe particles as waves. So I'll be discussing the theory part in the next video. Back to diffraction techniques. Here we use a radiation of a wavelength comparable with atomic dimensions. That is important to produce a resolution necessary to determine the locations and spacings of atoms and molecules. These spacings are typically of the order of 1 angstrom. Now, diffraction gives us information in the Fourier form, which can be analyzed in terms of the average spacing of lines and planes of atoms in a solid, the angles between the lines and planes, the symmetries of point groups, and with suitable interpretive skill, the location of particular species of atoms. The suggestion for the first time was made by von Lau in 1912 that a crystal might be regarded as a three-dimensional diffraction grating for energetic electromagnetic waves of a wavelength comparable with the atomic spacing, and that a diffraction pattern should provide information about the regular arrangements of atoms. X-rays are still the principal source of new information about the crystallography of solids and are supplemented by electron and neutron diffraction mostly. Now the energies of the three types of wave particles used for crystallographic work must be quite different if they are to have wavelengths suitable for their respective tasks. We can show that. For photons in the X-ray range, for example, as I can show you right now, lambda, that means the Broglie or de Broglie wavelength, can be written as C by nu. Now I have multiplied the numerator and denominator by h, so it becomes hc by h nu, and h nu is same as E. So lambda can be written as hc by E. Now if lambda is equal to 1 angstrom, that is the wavelength necessary to produce the important resolution. If lambda is 1 angstrom, then E is 12,000 electron volt. That means the X-ray radiations of the electromagnet, which are electromagnetic radiations, are quite energetic. Then we can see that less energy is necessary for a comparable de Broglie wavelength for electron. So that also I can show. So here for electrons, I have written the equation lambda is equal to h by mv, which is equal to under root h divided by 2me. So for lambda is equal to 1 angstrom, once again E is only 150 electron volt. It's about 150 electron volt, and the corresponding velocity is 7 into 10 power 6 meter per second. That means the energy for a 1 angstrom wavelength for electron is only 150 electron volt. An electron of this energy and wavelength moves at a speed of 7 into 10 power 6 meter per second. A still smaller amount of energy and speed is required for diffraction of neutrons by the ordered atomic array of a crystal, which also I can show here. For neutrons, I can write lambda is equal to h by mass of the neutron times velocity. So this denominator is nothing but momentum. So this is once again under root h divided by 2 mass of neutron into E. For lambda is equal to 1 angstrom, E turns out to be nearly 0.08 electron volt, and the corresponding velocity is for 4000 meter per second. So the energy is comparable, this energy is comparable with that of a quantized unit of lattice vibrational energy, which has a lot to do with the interactions of thermal neutrons. Next, I am going to discuss the uses of the three types of radiation or wave particles, namely the X-rays, the electrons, and the neutrons. So all these different types of wave particles shown here uh, have different though overlapping uses in structural studies of solids. All of them in fact interact with the periodic lattice subject to the same general geometric laws, which I'll be discussing in my next video. X-ray with photon energies in the range of 10 electron volt to 100 kilo electron volt can penetrate well below the surface of a crystal and form the basis for most of the conventional techniques for analysis of unknown three-dimensional structure. Now, since X-rays are scattered primarily by the extranuclear electrons, they are not too successful in determining the location of very light atoms such as hydrogen, but are very effective for the heavier elements unaffected by the presence of several isotopes of the same element. In X-ray crystallography, we are interested in the scattering performed by each electron moving in phase with the incoming electromagnetic wave and radiating coherently without any change of wavelength. The constructive or destructive interference of the coherent scattered radiation is controlled by the geometry of the interatomic level. Here I would like to uh, also mention that the scattering of an electromagnetic wave by an electron with no change of frequency, that means with no change of energy, was first described by J.J. Thomson and is sometimes referred to as Thomson scattering. Then inelastic scattering occurs also by the mechanism of the Compton effect, which you might have studied at your undergraduate classes. And this competes with the desired coherent scattering. Inelastic scattering provides an incoherent background of photons at all angles which are shifted to lower energies. Separation of the background from the coherently scattered photons of the original energy at the Bragg angles is an instrumental problem in structural analysis. The diffraction of electrons by a single crystal, as shown by Davison and Germer experiment way back in 1927, or by a crystalline film, as demonstrated by Thomson experiment, that too in the year 1927, are impressive demonstration both of the periodic structure of solids and of the wave particle duality of the electrons. Now, because an electron is a charged particle, it interacts I mean very strongly with matter and can penetrate only a few hundreds of angstroms unit into a crystal before it suffers either an elastic or an inelastic encounter. Thus, electron diffraction is ill-fitted to compete with X-ray methods for study of bulk structural arrangements. It is, however, well suited for two important tasks. Number one, the study of surface layers and surface states on crystals. The nature of the transition from a perfectly periodic lattice to empty space outside the crystal takes many forms depending on how the surface was prepared and what opportunities existed for contamination. Number two, the study of thin films. Here, we may well regard a sufficiently thin film as two surface layers with none of the bulk solid in between. And electron diffraction has been very useful in demonstrating some structural characteristics of matter in thin slices or thin films which deviate from the characteristics of the ideal single crystal. At last, I would like to discuss the diffraction of neutrons by crystals. The thermal neutron scattering from a crystal may either be elastic or inelastic, and both of them can either be coherent or incoherent. That means an elastic scattering may either be coherent or incoherent. Similarly, an inelastic scattering may also be either coherent or incoherent. Now, I already had mentioned you that out of the three wave particles, namely the X-rays, the electrons and neutrons, the neutrons are the slowest wave particles. Now, slow neutrons for which the Broglie wavelength is comparable with interatomic spacings can interact with a solid in several ways. In a non-magnetic solid, the interactions are with the nuclei only, since the neutron has no charge and has a mass much larger than extranuclear electrons. Coherent elastic scattering can take place subject to the same geometric laws as for X-rays or electrons, and this produces a diffraction pattern which differs from an X-ray one only in its improved efficiency for lighter atoms. In addition to the coherent scattering, neutrons will tend to be scattered in sorry. Uh, in addition to the coherent scattering, neutrons will tend to be scattered elastically but incoherently by the presence of more than one isotope of an element, which are randomly distributed over the atomic size. A more interesting process than this is the inelastic scattering of neutrons caused by displacements of the nuclei from an exactly periodic arrangement. Now, the energy of a neutron with a wavelength suitable for diffraction by a solid is comparable with phonon energies in solids that also I had mentioned earlier. Thus, the change in neutron energy and direction when an inelastic encounter takes place is larger and is readily measured. Now, since the neutron has a magnetic moment, additional complications occur when neutrons are diffracted by a magnetic solid. The cross section for the interaction of a neutron with the ordered array of magnetic electrons is comparable with that of neutron nucleon interactions. This elastic neutron diffraction can provide information about the distribution of magnetic moments. So in this lecture, which is a general type of lecture, I have tried to talk a little bit about the diffraction of the diffraction of various types of probes by crystals and diffraction as an investigative procedure. In my next video, I am going to discuss the general theory of diffraction. Hope you liked the video. So don't forget to like and subscribe. Thank you very much.